Okay, so today our lesson is going to be about a topic in Calculus 1 called related rates. And my name is Kurt Overhiser, and I'll be your host for this session. We'll be taking a couple of problems out of the textbook Single Variable Calculus by James Stewart, the 6th edition, in order to illustrate some of the concepts with related rates. Okay, so the way we're going to do this session is there are some dots on the side, and if you put your cursor or your mouse on those dots, you can listen to what I'm saying. And we're just going to go through these 7 steps that you see here one by one. So for the first step, what you're going to do is you're going to draw a picture of the situation. When you do related rates word problems, they are in essence word problems. It's an application of the derivative, and you have to read your word problem, and in many cases there's a picture that you have to draw. It could be usually it's a picture of a geometrical object, such as a rectangle or a sphere or a cone, something like that, and you want to draw a picture first. For step 2, once you draw a picture, you want to label that picture with variables for the quantities that depend on time. So usually you can, like if you're looking at for the height of a triangle, say, you can use the letter h for the variable that represents the height, and then put h in the diagram and put a little arrow to the height of the triangle. And you want to label all the variables that happen in your in the word problem. For step 3, you want to make a list of the given information in terms of the variables and their derivatives. So what this step basically is telling you to do is, once you draw a picture and label it, on the side of that picture you want to make a list, and in that list you're going to put a list of all the variables that you've introduced in the problem along with their derivatives. So like, for example, if you have a triangle that's expanding, then the height and the area would all be quantities that depend on time. So like in the previous step, I told you that you could label h for height, and as the height is increasing as time goes on, then you'll want to put a dh dt, and the dh dt represents the derivative with height with respect to time, and then you can put a number for that into your list. Okay, so for step number 4, what you're going to do is you're going to write down one or more equations that relate the variables that you labeled in your picture. And this is kind of the trickiest part, because, and the reason why it's tricky is because you have to know some basic mathematical principles that will allow you to write down those equations. I'll give you an example. One of the basic theorems that you might have learned a while ago in grade school was the Pythagorean theorem. It's the theorem that everybody knows is a squared plus b squared equals c squared, where a and b are the legs of a right triangle and c is the length of the hypotenuse. Other types of sometimes there's formulas for like a sphere or a cone that you'll have to write down. Like if you're dealing with a cone that's maybe growing or in size, its volume's increasing, then you'll have to know what the volume formula for a cone is. 1/3 pi r squared times h, for example. You'll have to know some basic geometrical formulas. Another way that you can come up with equations would be just to write down or using mathematical principles. Like a geometrical principle that you've used in geometry would be the fact that excuse me, the fact that corresponding sides of similar triangles are proportional, and you'll want to use the fact that they're proportional in order to set up a ratio as one of your equations, for example. Okay, so for step 5, you're going to, once you come up with your equation or equations, you want to differentiate them with respect to time. And in most all cases, you're going to be using the chain rule. In fact, you'll be using a form of implicit differentiation, meaning that all those variables that you wrote down in your, labeled in your picture that depend on time, you're going to be taking the derivative with respect to time, where time is an implicit function of the variables that you've chosen. Okay, for step number 6, you want to, once you take the derivative of your equations, you're going to substitute the information from your list into the resulting equation or equations. That's pretty self-explanatory. You're just going to plug in numbers, basically. For the final step, number 7, you're going to solve for the unknown rate of change. And we know from calculus that when we talk about rates of change, they can be interpreted as derivatives. So you're going to be looking for, usually the word problem will tell you to find some unknown rate of change. And so anyways, let's go ahead and get started, and we'll work a couple examples from the James Stewart. Okay, so the first problem that we're going to look at is going to be on page 186. We're going to look at number 4 from the Single Variable Calculus 6th edition by James Stewart. This problem says the length of a rectangle is increasing at a rate of 8 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing? Okay, so we're going to illustrate these 7 steps for you, and we'll label them. The first step is to draw a picture. Step number 1 is to draw a picture of the situation. Well, the situation is we're dealing with a rectangle, so we better draw a small little rectangle here. And step 2, right after it, is we need to label the picture that we just drew with variables for the quantities that depend on time. So you can see that the width is increasing at a rate of 3 centimeters per second. So the width depends on time, and the area depends on time. So let's denote x as the length and y as the width of the rectangle. So we've labeled the picture with the quantities that depend on time. Now we're on to step 3. I'll put step 3 over here, and we're going to go ahead and make that list that we were talking about. And in this list, we're going to put the given information in terms of the variables and their derivatives. So the information that's given would be that the length is 20 centimeters. So we write down x is equal to 20 centimeters. The width is 10 centimeters, so we've already said that y is going to be our width. So we write down y equals 10 centimeters. And then there are two rates of change here. It says the length of the rectangle is increasing at a rate of 8 centimeters per second. The length of the rectangle is increasing at that rate. That means we're dealing with a derivative. So we can write down that the derivative of x with respect to time is equal to 8 centimeters per second. And also the width is increasing at a certain rate, so that represents the derivative of y with respect to time, and that rate is going to be 3 centimeters per second. So you can see that we have used all the numerical information that's given in the problem. We've made our list with 4 things in it: x, y, the derivative of x, and the derivative of y. Next, it says the problem indicates that you have to talk about the area of the rectangle. So when we get to step number 4, step 4 says we have to write down an equation that relates the variables in the picture. Since the only variables are x and y, and we have to find how fast the area is increasing, it makes sense to just write down the area formula for a rectangle. So we write down area equals x times y. And that's the only, and this situation is easy enough because we only need one equation for this problem. Step number 5, we're going to take the area equation and differentiate it with respect to time. Notice that the area equation is a product of two quantities, so we're going to have to use the product rule here. So we can write down the derivative of area with respect to time is going to be equal to dx over dt times y, plus, we have to put a plus in here because we're using the product rule. Next, we're going to take x and multiply it by dy dt. So that's the end of step 5. Okay, for step 6, we have to plug in all the information in our list into the resulting equation that we got in step 5 as a result of differentiating the area formula for a rectangle. So plugging in all this information, we get dA dt would be equal to dx dt, which from our list is a numerical quantity of 8, times y, which has a numerical quantity of 10, plus x, which has a numerical quantity of 20, times dy dt, which has a numerical quantity of 3. This gives us 80 plus 60, which is 140, and then we have to give this units of measurement because we're dealing with area with respect to time. Area is going to be measured in centimeters squared, and we're going to divide it by seconds. And this is the final answer to the problem. This is step number 7. Step number 7 says you solve for the unknown rate of change. In this case, this problem was simple enough in which we actually didn't have to solve for the unknown rate of change, because once we plugged in all 4 pieces of numerical information into the derivative from step 5, it was the dA dt, which was what we're trying to find, was already solved for us. So in this case, step number 7 just kind of fell into our laps. Okay, so for our second example, we're going to be doing number 12 on page 187 of James Stewart Single Variable Calculus Textbook, 6th edition. And this problem states that if a snowball melts so that its surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. So step one, we have to draw a picture of a sphere. I'll try to draw a picture of as round as I can. So there's a three-dimensional sphere, and here's the center of the sphere. We have a radius, and then we also have the diameter. We'll call it capital D. So step one is our picture. Now step two, we've also labeled the picture. Now for step three, we want to make our list of all the given information in terms of the variables and their derivatives. It says the surface area decreases at a certain rate. So we're going to use A for surface area, and we'll call it, because it's a rate of change because of the centimeters squared per minute, we know that that's going to be a derivative. And so we'll call that the derivative of the surface area with respect to time. And that's going to be equal to a numerical quantity of -1. Now the reason why it's a -1, the negative is because the fact that the surface area is decreasing, it's going down at a rate of 1 square centimeter per minute. And then the only other piece of information we have here is the diameter. Diameter is going to be 10 centimeters. And we've exhausted all the information that's in the problem. So we go to step 4, and we start writing an equation that relates the variables in the picture. So this is a three-dimensional sphere. It talks about its surface area, so we're going to have to write down the surface area formula for a sphere. And that formula is given by 4 pi r squared. 4 times pi times the radius squared will always give you the surface area of a sphere of radius r. Notice that in step 4 it says write down one or more equations that relates the variables in the picture. Well, we have one equation, and we're going to have to write down another equation. We have to figure out the relationship between a radius and a diameter, and that's a pretty simple relationship. The diameter, of course, will always be equal to 2 times the radius. So in this case, we've got two equations in which we're going to have to differentiate with respect to time. So we're ready to go to step number 5, and we differentiate with respect to time. So we're going to find dA over dt, and using the power rule here, we multiply 4 times 2 to give us 8 pi times r, and then the chain rule says we need to take this and multiply it by the derivative of r with respect to t. So that's the derivative of the first area equation. To find the derivative of the diameter equation, would be simple enough. We take the derivative of the diameter with respect to time is going to be equal to 2 times the derivative of the radius with respect to time. Okay, so we're on to step number 6, and we're going to substitute the information from the list into the resulting equations. Okay, so for step 6, we have the diameter is equal to 2 times the radius, and so of course that means since the diameter is 10, the radius is going to be half of that. So we plug this into our equation and we get r is equal to 10 divided by 2, which equals to 5 centimeters. Next, we take the derivative of area with respect to time, and we're going to take that down here and we're going to plug in our quantities. From our list, we know that dA dt has a numerical quantity of -1. Set it equal to 8 pi times r, which we found was half of 10, which is 5, and then times dr dt. So solving for dr dt, we get -1 divided by 40 pi, and then next we take the derivative of the diameter with respect to time, and we bring that down here, and we see that this derivative is going to be equal to 2 times -1 divided by 40 pi, which is going to give us -1 over 20 pi, and that is going to be in centimeters per minute. And this right here is our final answer, because we were supposed to figure out the rate at which the diameter decreases, and notice that this quantity is negative, so that means that the diameter is in fact decreasing, and that would be our final answer. And so that is step number 7. Okay, so this concludes the related rates portion of Calculus 1, and good luck in your studies. Bye-bye.